keep posting questions in the chat box. And once the presentation is over, so that the flow does not get disconnected, I will attend to all the questions, whatever it is. And it is a new area. So maybe many questions I don't know the answer, or there is no direct answer also available. These are some things which we all have to jointly evolve and keep going. Okay, so with that, so let us get into the topic. So today, laser post-processing of additive manufacturing is my prime focus. Along with me, he is now Dr. Shashank Sharma, who was earlier a PhD scholar. Now now he is in US working in the area of additive manufacturing. He was a PhD scholar with me. We developed the laser post-processing during his PhD stay at IIT Kanpur. So when we are looking at the content for today's lecture, first is need for post-processing in metal additive manufacturing is very, very important. So what is the need? And today, additive manufacturing, and that too metal-based additive manufacturing, is now becoming the talk of the town. So many wonderful products are getting developed. So many functionally graded materials are getting developed. So many composites are getting developed. And they develop it through additive manufacturing, and then they do heat treatment, and then they do, during the heat treatment, they try to play around with precipitation hardening. All these things are now carried about. So the need for post-processing has become a vital role. Initially, when additive manufacturing was talked about in polymers, the post-processing, what we were trying to talk about is only cleaning the sample and also giving coloring to the sample. Today, from there, we have gone sky heights, which you cannot even imagine. So that is where. So the need for post-processing is very important. Next is post-processing in metal additive manufacturing. We will see some of the literature which are available for laser polishing. Then we will try to review on laser polishing of metal additive manufacturing. The first one, when I say laser polishing, this is for a alloy, this is for a metal, not by a part which is made out of additive manufacturing. Then I will move to review on laser polishing of additive manufacturing. Then few of the process parameters as far as laser polishing is concerned. Then I will try to give you a very fundamental insight on laser matter interaction, which is very important. If you can understand this laser matter interaction, then you can try to solve the problems, whatever you are given or challenges thrown in front of you. Then the next thing is understanding melt pool convection. Some of the key parameters. Mathematically, how do I formulate such that I can do some computation and try to get the best out of it? Then hydrodynamics, which are involved in the process of polishing. So melt pool and hydrodynamics, these two go hand in hand. So melt pool, hydrodynamics, and then conclusions, and then scope for the future. When we look at need for post-processing for metal additive manufacturing, there are two processes in front of you. One is called as the powder bed process. The another one is called as DED process or DMD process, whatever people say. So direct energy deposition process, and you have a powder bed fusion process. In powder bed fusion process, you should understand the container size which is there on the left side or on the right side dictates the material what it has to be there in the center portion. Okay, so the center portion is where you get the output. So a laser is focused on the center portion, which I called it as build platform. So it is the build platform sinks down, the table goes up, and the roller tries to drive and take one layer thickness from here to there. So now what are all the challenges? First biggest challenge is what should be the layer thickness. The layer thickness sometimes can be few microns or sometimes few hundred microns. So you try to pull that few hundred microns and bring it to the build platform and then allow the laser to get exposed. So you try to build one layer and the rest of the residue material will be pushed onto the other side of the powder bed. Other side of the powder bed, you try to get it. Okay, so here you have this, the lead screw of the roller, whatever is there, that puts a resolution. Second thing is the powder size puts the resolution. And the third one is what is the laser when it is trying to hit at a surface. It is, if you try to take it in a 2D plane, it is an ellipse or it is a circle. But when you try to do a 3D profile of it, you will have a Gaussian distribution. When you have a Gaussian distribution, now what is happening is between two layers, there is always a stitching happening. Okay, so once the stitching happens properly, then you get a sound quality product. If the stitching does not happen sound, so then what will happen is you will try to have defects there. So the roller leveling roller, the powder size, the laser power, the laser stitching, the three things are very important to make sure that one single layer is formed. When we are talking about all these layers, we are trying to use an XY coordinate system. But when you try to have a three-dimensional object and which is not prismatic, right? You will always have a radius which is cutting across. Moment you have a XY movement and there is a radius, there is always a error which is there. That error, they always call it a staircase error. This staircase error gets amplified when you start building it larger and larger and larger. Okay, so that staircasing error you have to reduce. So if you want to reduce, then you have to look forward for post-processing. And next thing is you have developed completely an object. Now this object, if you want to make it something like a coating on top of it, you can try to do. Or if you want to do, already there is a insert which is available. You want this object to get inside the insert, so you can try to do. The third thing is, of course, you can start playing with the heat treatment and trying to remove some of the defects. So these are the needs which push us forward in the laser powder bed fusion method to go for post-processing in additive manufacturing. When we talk about direct energy deposition, you have a laser. You have a laser which is coming from one side. Excuse me. You have a laser beam which is coming from the center. You have a shield of gas which tries to prevent the laser getting shattered here and there, and it also tries to focus you to a small point. Then you have two feedback sensors which tries to collect the temperature as well as the spectroscopy analysis in understanding what is the nature of the material which is getting deposited. So here we don't have a problem like whatever we are talking about with the leveling roller. Here you have one problem is like the table platform, either it can sink down or it can grow up. So there you will have the same problem like here. So again, rough surface. And when you start working with metals, what happens, you should understand, you will never get a very small smooth wire, smooth layer. You will always have some amount of spatters which are there. So you should be very careful that you should remove all those spatters. Apart from this, wire arc machining is also wire. Arc or wire assisted additive manufacturing is also possible. However, it has not got so much of popularity as compared to these two processes. So I am trying to talk about this, and wire, if you can understand this properly, then wire additive can also be done very easily. Okay, so these are the two processes which are predominantly used apart from wire for additive manufacturing. So now I have pushed you to tell you what are all the needs for doing the post-processing operation. So when we look at the needs for post-processing operation, you can see that the powder in one layer, if you see the powder, how is it there? How is it deposited? So you can see sometimes the powder is not melt, sometimes the powder melts and forms globules or galling or balling. All these things are possible. So if you look at the laser powder bed fusion, you will have such spots which are there. Okay, when you try to do the AFM image, or when you try to do the three-dimensional topography, it is 2D and this is 3D. You can see what amount of variation is there on the surface when you try to see it. They are talking about somewhere around about 129 microns. The height will be somewhere close to 100 microns. Okay, so this is accumulation or joining of powder, then melting of powder, then it forms. When we go to direct laser direct energy deposition, you can see undulations on the surface as compared to that of powder. Here it will be the error, whatever it is getting formed dimensionally, which will be more prominent than that of the laser powder bed fusion process. So these are some of the SLM mechanism, that is When we talked about this powder bed, there are two types of processes which are possible. One is called as SLS. The other one is called as SLM. The other one is called as SLM. So SLS means selective laser sintering. There is a possibility that these two the powder particles can join, but it need not join 100%. So you might have some small voids in between. Sintering means along the boundary of the abrasive, you start a joining process. So many a times you will have small undulations on the surface or small porosities on the surface, which tries to bring in irregularities or defects in the process. When we try to do selective laser melting, it is not sintering, it is melting. So 100% the powder particles are melt and it is allowed to join. If you want to get a sound, good quality product, we always go for selective laser melting. Of course, there is an energy balance you have to do to get the required output. So what are all the materials which work in SLM process? Titanium alloy, stainless steel, cobalt, chromium, then TI6AlB4, Inconel, then we have ALSI, then cobalt, chromium, and 31CL. So these are the stainless steel. So all these things are processes which they work under SLM process. And generally, if you see the surface roughness, what it gets generated, it is somewhere between 5 microns to 10 microns. So when we say 5 micron to 10 micron, and if you look at a rough surface, now higher the surface roughness, higher will be the points where it is trying to join, and then you will have a lot of stress concentrated points. These stress concentrated points over a period of time of exposure or fatigue loading will form a crack, and it will try to grow further and it will try to break. The other way around is in that small trenches, you might have some OH particle, or you might have some other acids which are going there. When you put in service condition, it tries to corrode. So in order to prevent all these things, the surface roughness is reduced to a large extent. When we talk about direct energy deposition, you have again stainless steel, TI6AlB4, TI alloys, and Inconel 625 alloys. So these are some of the things which are available. And predominantly when we try to look at polishing, we try to take this property and then we try to play around with this property and try to reduce this roughness from 10 microns to 1 micron or less than 1 micron. So that is what is the major challenge we are looking forward. So if you look at what are all the different types of defects, so you can see that these are some of the defects. Let us see one after the other. Staircase effect. So this is a staircase effect, whatever is seen here. The layer thickness, surface slope, particle size, and material. These are some of the process parameters which lead to staircase effect. So experimental condition, it was done the SLM slope 90 degrees, and then we also done DED was also done 60 to 65 degrees. So I'm trying to talk about 90 degrees means perpendicular, 65 means at an angle. So next is track overlap. In track overlap, what happens? The hatch spacing and the layer thickness material is always like that. Then you have this balling effect. Balling means you try to form something like balls. So the laser power, scanning speed, particle size, and materials, they all join together and they form a balling effect. Okay. Then the humping effect means balling is small things. Humping is a large thing when you have. Humping effect is a laser power, scan speed, and material. These are all there. They join together and form. Next one is partial melting of the powder. When we try to move it at a very high feed rates or a lower power, this will try to form partial melting, and this also leads to some amount of defect. The next one is going to be ripple effect. Ripple effect is again going to be part of like the ripples are nothing but something like waves, cylindrical, like circular waves, or up and down waves are there. So ripple waves, laser power, and scanning speed, material, these are also part of it. Okay, these are all the process parameters. These are all the surface defects. All these surface defects have to be covered by this by a process which is exhaustively used for finishing. Then you have surface cracks. Okay, when we talk about surface finish, These are some of the surface finishing process. These are some of the surface finishing processes. So if you talk about the surface finishing process, so when we talk about the surface finishing process, it is very much used for the surface finishing process. So these are all the different types of surface finishing process. The surface finishing. Okay, so finishing process, you will get to have mechanical finishing process is abrasive flow finishing process. You have magnetic abrasive flow finishing process, abrasive fluidized bed finishing process. You have ultrasonic cavitation finishing process, and you have hydrodynamic cavitation process. All these things, all these processes are mechanical force dominated, and these forces they try to exert on the free surface, and it tries to react with the free surface and try to remove the undulation on the surface. Next one is going to be chemical. So we can try to think of chemical polishing, we can think of electrochemical polishing and plasma polishing. So these are the three things which are working. So chemical polishing. So all these things predominantly it works on chemical and electrochemical process. It also tries to remove undulation on the surface, but the amount of material removal in chemical based and electrochemical based is not as high as compared to that of mechanical. The last one is going to be laser and electro beam machining process. These two processes use predominantly thermal energy to melt the surface. The advantage of these two processes are you can try to focus the energy at a small point. You can do selective finishing or selective machining or whatever it is, selectively you can do, and then you can try to do internal, external by changing the focal plane. All these things you can play around. So laser and electron beam is the most prominent one, which are now gaining a lot of popularity. When we look at all the finishing process, you have seen abrasive flow machining process, magnetic abrasive machining process. You have USALP and HCAF, and then you have EPC, then you have LP. So all these processes are finishing process. Here they have talked about the material which is removed. So initial surface roughness are around about 25 to 30 micron and 17.4 micron, and then finally finished is 0.5 micron to 1 micron. So 14.2 is the final roughness surface finish. So here when we talk about remarks, so you can also see that requires higher number of passes. So what I'm trying to say is, if you are trying to do AFM, abrasive flow machining process, number of strokes is called as the number of passes. Okay, so it takes less than 1 hour, it takes 3 hours. UCAF takes 45 minutes, HCAF takes 40 minutes, less than 40 minutes. And when we are trying to talk about LP, which is laser polishing, it tries to do very fast, very smooth, and try to get the best out of it. Okay, so these are all the processes. So we are more focused towards laser polishing. Let us now discuss more on laser polishing. So laser polishing is a laser-based post-processing. Laser polishing, if you try to move a laser on top of a surface, so this is what is the initial surface roughness. Okay, so initial roughness is that, and the next one is the redistribution of surface as per it is. Then you will try to see polished surface polishing, and then you will try to see the laser and how does it interact. So when we are talking about initial surface topology, so you see that you have the sharp peaks. Now what we are trying to do by using laser, you either focus or you try to defocus. When you focus or try to defocus, what happens is when you try to defocus, the energy gets distributed in a plane. When the energy gets distributed in a plane, the flux intensity goes down. Once the flux intensity goes down, so now it will not melt and vaporize. It might go to a stage of melting and then depositing there itself. or it can deposit. It can try to deposit, and then it can try to melt. So this is what is very important. So when it melts, it tries to just help in resolidification. So what happens is when you try to melt, and then there is always a liquid which is there. This liquid undergoes some surface tension. So this surface tension, what will happen is it will try to flow or it will try to roll up. So when it rolls up, it tries to have a higher roughness. When it does not roll up, it will have a better roughness. So if you look into it, this is what is the analogy for the laser post-processing technique. So the laser, you can see red color, the red color laser polishing peaks. Peaks are available. அதுக்கப்புறம் கீழே தானே so here if you see that this polishing takes place, and then you can see how does it go. These are the peaks, and these are the blue peaks which we get after the polishing. Okay, so you can see these are the ripples which I told you here, ripple effect. You see a ripple effect. So this is what is a ripple effect, like a wave which is getting created. And undercut are also possible. See, when there is a difference in radiation level and other things, what will happen is some of the metal which gets vaporized, the other metal will try to flow inside and do. When it tries to flow inside and do, it will try to form a large bump. So that is what. So this is what is called as undercut. You can also have bulbs, you can also have structured systems. So these are some of the laser. When the different types of polishing, when it is done, it tries to reveal the surface. Okay, so you will have rough surface, ripple surface, undercut. You will also have this thing, step structures. Okay, and when we try to look into bulge formation or track, you can see that graph. This is the bulge formation. So this is what is a bulge formation. Generally, bulge formation are formed when the ripples are formed and they are moved. So it tries to solidify and then try to get the ripple shape. So this is what is bulge formation and track overlap. So you will try to get this A, B, C, D. All these things are tracks which are used. So code A, code B, code C, all as received. Then we have SA, surface roughness. And then we have a then we have this is the surface area. This is the deposition energy. You can see predominantly happening here. Okay, and so this is the before polishing and this is after polishing. And here what will happen is you will have a laser typical polishing results, and then you get the surface finish here. So now when we look at some of the literatures which are available for post processing with metal additive manufacturing, here I have put they have used continuous laser, pulsed laser. These are all the workpiece material which have been tried. Initial roughness is 10.4 and final roughness is 2.4. So much of reduction happens. So you can see here from 0.206. See, you can't get all the time from 10 to 1 micron. You have to do step by step. Maybe 10 to 2.4 you have, then 2.4 you have to start doing post processing, and then you might go up to 1. So 1, it goes up to 0.1, 10 goes to 1.4, 5.2 goes to 0.3, 5.4 goes to 0.06. So now when we are trying to look into this in a deep microscopical language, we try to get the melt pool simulation. Melt pool simulation, basically what happens is when you try to hit the laser, when it tries to hit at the laser and the laser is also moving, there is a gradient which is getting formed. Because of the gradient which is formed, there is a surface tension gradient which happens. This surface tension gradient, what it will do is it will try to suck it inside or it will try to pull it out, depending upon the situation over there. If it is gradient there and the suction is pulling outside, then you will always have a dent in this surface. So These are wave decay, these are new decay, these are small incorporation, these are balling. These are keyhole defects. Keyhole defects happens because of melt vaporization phenomena. So when we try to do that thermocapillary melt flow simulation, we see that when the laser tries to hit at the workpiece surface, how does it melt and how does it move? Okay. While a number of advancements were made over the recent years in the modeling of laser polishing process, it is absolutely clear that the thermophysical mechanism and the dynamics are still insufficiently understood. While this type of comprehensive laser polishing models are still in existence, it is reasonable to expect that they will eventually become reality in the near future. This is what is a quote given by Mohajirani in 2018, very recent paper. So if you try to see the laser, you can see that laser. It is the radius. This is the H nu p, that is the convection which is forming there. They form a current and then it is getting formed. This is the complete melt pool and this is the heat affected zone. When we are trying to talk about laser polishing, so these are some of the important parameters which are there. One is the laser intensity. It should be 10 to the power 9 watts per meter square. Then you will have a scanning speed 500 meters per second. Pulse width is microseconds to continuous wave. Track overlap is 50 to 95. Pulse repetition rate is hertz to kilohertz. Then you will try to focus, defocus. This is a defocus one. So when we have a moving laser trying to create, this is a rough surface. Okay, this is a surface tension gradient driven driven flow. So then you have a solidification front. We have a solidification front. You have and the gradient, surface tension gradient driven flow is done by this. Okay, so you can see here. This is what is a Marangoni effect. The current is formed and the drive goes from left and right. So these are bulk substrates. So you have shallow. These are all shallow melting. Okay, these are all surface tension gradient induced suppressions. Then you have surface over melting. So these are the three possibilities when you try to hit a laser on the surface. So you can have shallow melting. That means to say very small melting can happen. The next one can be this. The surface tension gradient induced suppression. Induced suppression. This is the other thing which you can have. Then you can have this surface over melting. So wherein which you will have all these things melt and then you will have such close things. So these are some of the problems which are faced which are placed by the surface laser polishing. So now you know this is what, this is what, this is what. So now you can very easily try to maintain what is required from the output. So now the advantage of laser is today these lasers are fixed with 5-axis machine and 6-axis machines. So it can try to take an orientation in any direction you want. In any direction you want, it can try to take, and it will also try to do all these things. Just by playing with the parameters, you try to have a better control. Okay, so and the track overlap is, see, laser intensity, you guys understand what is laser intensity. Pulsed with this, there are two types of laser. One is continuous laser, pulsed laser. When you have pulsed laser, the energy levels are very high for a small duration of time. So when we are looking for melt vaporization or melt and flow, this is always very much used. So this is one of the parameter which is very efficiently used. Okay, so here we try to play a very, very important role. So the next one is going to be overlap. So scanning speed is nothing but like your feed rate. So as the feed rate increases, the overlapping spots distance will increase. Moment the overlapping spots increases, then it is also going to create lot of ripples in the problem, and this will try to lead to a lot of defects, and these defects have to be closed, which is going to take more time. So this is the other thing which is very, very important. So these two are very important, and overlap of tracks is from one line to the other line. In a single line, scan speed comes a very important role.
Bharat?
Yes, sir.
We are unable to,
Cut.
yeah. Wait for some time. I think we lost the connection, I guess.
Oh, Subbu, I lost connection in between.
Yes,
Subbu,
yes,
I'm
sir,
reconnecting.
Yes, sir.
I'm reconnecting. Make me to share, Subbu.
Yes, yes, just a minute. Yes, sir. Now is it fine? I'm made you as a host, sir.
Yeah. So just give me a minute.
So are you in the lab, sir?
Yeah.
Manufacturing lab? Yeah, okay, sir.
Yes. So just 1 minute, Subbu. Okay.
Meanwhile, participants have any queries so far, whatever professor discussed?
Yes. So it has come once again. Sorry.
No problem.
So is it visible now? Yes.
Yes, sir. Clear. Sir, could you please? Yeah. Now it went to presentation mode also. No problem.
Yes. So now, if you look at it, this is what is the pulse width. I said pulse width is higher. Then it is repetition rate. Repetition rate is also very important. At one spot, how frequently you hit, what is it? And then I have said also defocusing. Please don't go with the impression that only focusing has to be there. If you can play with defocusing, that is also allowed. Finally, what do you want? You have to melt the material, allow the material to spread. And once it spreads and it solidifies, your roughness increases. So this is what happens here. So these are all the important parameters which are there. And I have already talked about laser, microsecond laser to continuous laser. Galvo scanner, F theta lens I have talked about. Melt spool I have also talked about. So if this is what is the initial surface, final surface finish after laser polishing, what do you get is what is shown here. So what are the research gaps? The role of melt hydrodynamics during laser polishing is not clearly defined, is very unclear. So this is a very important finding which we have to take it and go in the future when we are trying to do some analysis. The next one is the process parameter for optimization is also very less. The is redundant as the roughness reduction, the initial surface completely changes. So this is the other biggest thing which is there. The next thing is the extensive experiments are required to locate the optimum conditions for varying substrate materials. So this is also very important. So this is another thing which we are always focusing for about. Okay. So this is another interesting thing which is not very much covered. So this is also the other biggest negative thing which is there. So the next one is the numerical modeling of actual process. Actual process is also not very famously seen. So we are looking forward for alternatives for this. So these are some of the research gaps which are available as of today. So now first let us understand what is laser matter interaction. So laser matter interaction is you have to first understand what is this laser matter interaction. So laser matter interaction basically talks about what happens when the laser comes in contact with the surface. So first, when the laser comes in contact with the surface, the heat, whatever comes and hits, so when the laser comes in contact with the surface, first the heat comes and hits the surface. When the heat comes and hits the surface, immediately there is a conduction phenomena. So the atoms vibrate, and once the atoms vibrate, the heat gets dissipated, moves to the next lattice to the atom, it keeps on going. So now, if you try to figure out what is the speed in which the heat gets traversed in the between the atom and the lattice, and between the heating and hitting and going, if it is going in this way, so then you can try to find out an optimum way. When will the heat be absorbed? When will the heat be dissipated? So this is what is, so absorption of the laser on the workpiece, then the laser is getting transferred, the energy is getting transferred onto the, see, laser hits, the energy transfers, because heat has to be transferred. If the heat is not transferred and if it is getting accumulated under one spot, it is going to be melt, vaporization, like sublimation. But generally what happens, the heat gets conducted in the workpiece. Moment the heat gets conducted in the workpiece, then comes the manifestation of heating in the bulk. Then there is a gradient which is formed. Once the gradient is also properly derived, then what we do is we try to move for the onset of melting. Then there is a thermocapillary and capillary induced melt convection. Melt convection is what you have a temperature difference in along the z direction. So top surface is cold, bottom surface is top surface is hot, bottom surface is cold. So there is a current which is getting created. This current will try to form, will try to circulate, and this circulation, what it will try to do is it will try to move the material up and down, up and down, up and down. So when it is trying to move the material up and down, there is a thermocapillary action which is dominating, which comes into action. On top of it, what happens? The laser, when it tries to hit at a surface, and then when you try to hit at a surface, and then the current keeps moving, the melt pool keeps moving here and there. When the melt pool keeps moving here and there, it will try to form ripples. And in the meantime, at the laser, when it tries to interact with the material, there forms a plasma, and this plasma also collapses. Moment there is a collapsing of the plasma happening, there is always a recoiling pressure which is applied onto the liquid, and that forms a ripple on the surface. So now that is getting formed. Then the material is getting expulsion starts. So it forms a ripple, it forms like a muddle, and then goes. The laser is switched off, then the melt convection and solidification starts. So if you look at it, the laser matter interaction, these are the steps which are generally it is undergoing for creating a rough surface. So so this is what is very important, and this is what you should understand. If you could understand the complete cycle, then even before all these capillary this and that could happen, if we could move this very nicely, then you will get a very good surface finish. So this is the other interesting thing which is there. So now this is what it is when the laser is trying to hit at a surface. So this is how the plasma will get formed, the plasma, and then the light gets totally internally reflected, and then it will try to form, the expulsion is trying to get formed. So you will have a melt pool which is there, and this melt pool is so when it is getting thrown out of the surface, it forms melt scatter, and this is the Marangoni convection. So this is Marangoni convection which is there. The capillary forces are dictating. You will try to have, these are all the melt flows, these are all the vapor flows which is happening when the laser matter interacts with the surface. So understanding melt pool convection water wave analogy, it is like this. So when we try to do that, you see that. So when this is an analogy. So water drop hits, so you will see the ripples getting formed. And once the ripple getting formed, it tries to form the higher end. So let me do it once again. You will see that. So when the see now when the laser spot hits, it will try to when the laser spot hits, it will try to form ripples. Okay, then this ripples will form, and you can see one more ripple which tries to pull it up. So once you freeze it, all these things are common for laser also. It is a very similar analogy which is used. So this is very interesting. Let me play you once again. By looking at it, you will try to understand. This is one. These are all recoiling ripples which are getting formed. Okay, and there is a spatter which is getting formed, so the material is getting absorbed. So now the entire wave goes down. Once the wave gone, the ripple forms, and then it forms something like a center ripple is formed. So it can go up, and you can see how the light is thrown, and then it can try to improve the surface. So look at it; it goes down, and then it tries to form the ripples. Okay, so the key parameters when we talk about our laser intensity, pulsed duration, thermocapillary force, the evaporating heat flux, recoiling pressure, and surface tension. These are all the key parameters which are effectively used, in the this thing. So then this is what is the this all the parameters plays a very important role, and then we try to look into what is it. Okay, so all the surface tension is also very important. Recoiling pressure is also very important. Evaporate to heat flux, with vaporization, cooling of the subsequent melt surface, resulting in temperature dependent multidynamics, is the evaporate to heat flux, which is also very important for you to consider. So when we try to do a numerical simulation of the same, this is the numerical simulation. You can see here boundary condition, and other things are also used here. Okay, so no slip condition, melt pool, the vapor plume which is getting formed. These are the free surfaces. So this is how it forms. This is how you get a spatter. So the assumptions made generally which are made is flow of the liquid. Flow of the liquid is this thing. So the flow of the thing is very important, and then we try to do it the incompressible flow, and then the next one is metallic vapor. Metallic vapor is getting formed. So metallic vapor is regraded as the ideal gas. Plasma formation and the multiple reflections are there. So and then you will also have all thermophysical properties are in nature. So all these things are there. So now then the laser absorption, you use the following equations for laser absorption. So multiple reflection is something which is very unique, which you have to look forward. Where we have to look forward, and then the next one is the Fresnel lens absorption, implement that F theta lens. So that is also so that is very important. So this is the other thing which is there. So the next one is going to be the Fresnel lens. So this is the other thing. Then heat impact, whatever is there, it is going to be there. So that is the other thing. So here we talk about rho with respect to conductivity with respect to temperature, and then we have Cp with respect to T, phase change which is there, and the other things which are very important are being discussed. So then phase radiation, then ambient heat transfer, Then we also have evaporation heat transfer. So this is very important for all those things, right? Next is melt pool convection. So the lamellar flow module with temperature dependent thermophysical properties, mu T and other things are there, and you have Marangoni convection, you have vaporization due to recoil and free surface. All these things we have considered in our model and we have published it. So free surface handling, ALE was used, level setting was done, and the phase shield was done. Adaptability with changing phase laser operations was done. Realistic values of thermophysical parameters were considered, and we got the output. The numerical simulation, the heat transfer and lamellar flow governing equations were this, and these are the boundary equations. These are straightforward cases. When we try to do a moving interface, so it is ALE algorithm was used, and then we were trying to get the required output. So these are the smooth surfaces, and the level sets were done so that we can get the required ones. So these are alternative ALEs which were done, and then we got the output. So the fundamental hypothesis of laser post-processing is, so we try to heat the surface and we try to do the melting of the surface. It was trying to move here and there. And then we have the reduction in the asperities height due to thermocapillary actions which were trying to look forward. So then these are some of the shallow surface melts which were done and the capillary actions which we did. So we did for a single asperities, and then we try to hit at a surface. So then we try to see how does the surface tension come into effect, how does it move, and then how does it create. So now you see from here it started, it moved, and then it finally formed a ripple, and then you got the final surface. So these simulations were done, and then we try to understand what is the results of that. The suppression of the suppressed asperities, thermocapillary regime was also considered, and we try to get this type of results in our applications. Okay, so these are some of the numerical results. They found brief shallow melting was done. Brief shallow melting was done. The capillary forces prevailed with the redistribution melt. Then during thermocapillary regime, you have Marangoni forced induced homogeneous distribution of melt ablation. Then thus capillary regimes can be used for redistribution of microasperities. Thermocapillary regimes should first choose to facilitate reduction in the peak, and the choice of the laser power depends on the initial roughness. So surface over melting is keyhole regime helpful. So this is the other thing which we try to remove and see. And these are the keyhole effects what we try to do. And then we figured out, yes, the recoil pressure induced shallow keyhole procedure of sound waves. These oscillations will continue throughout the laser scanning while it is used. Amplitude of these oscillations in case of 70 microns was tried. And then we also tried to see the RZ values. So these are the cutoff length is 2.5, evaluation length is 12.5. We try to see what is the surface improvement in the horizontal direction and the vertical direction, and see what is the improved output. So the process parameter selection via numerical simulation. We did a thermoplastic induced suppression asperities were done. Then laser beam was defocused by 10 millimeter. Then the scanning speed, initial topology was done, and the experiments was done. So these are the two different. Unpolished surface was black and polished simulation was blue. And we were trying to get the results validated with the experiments what we conducted. So surface topology, spatial surface topology, we got the results. So these are some of the experiments which were conducted, and this is what it is. Initial roughness was 7.8, horizontal, vertical, we were able to get 1.5 and 1.6, and RZ values were there. So to come to the conclusions, the shallow surface melt, the reduction in peak to trough amplitude is not prominent. The thermocapillary regime effectively reduces the peak to trough amplitude. The keyhole regime produced surface values much larger than initial RZ. Then the developed model has proved to be effective as compared to that of others. Up to 85% reduction in RA and 91% reduction in RZ were achieved by this methodology. The scope for future direction, with the help of advanced characterization facilities, depth variation for 3D roughness should be thought of. Combination of CAD and numerical simulation should be used to plan the laser tool path. The laser planning should be linked to the initial surface roughness of the component. The unwanted effect of melt pool needs to be addressed with the help of the numerical simulation. So with that, thank you very much for the opportunity. I am open for questions. If there are questions, we can try to take it.
Yes, thank you, Professor. Thanks for a excellent talk. Actually, we have been learning a lot from Monday, past 4 days, related to your lectures. You insist more upon numerical simulation, and then in that also how you introduce a CAD data, that also insist a little more. That is really nice, sir. Yeah. So with this, like to request the participants to pose the question. Do you have any? You are allowed to unmute and then ask, or otherwise you can write it in the chat box. I will take up the questions for you. Yes, somebody?
Yeah, feel free to ask. Whatever is related to laser processing or additive manufacturing, go ahead and ask.
Good afternoon, sir. This is
Yes.
Pramod
Yeah.
from IITPKD. Sir, it was a very enlightening presentation, sir.
Thank you.
Sir, I had one question, sir. When you were defining the defects, sir,
Yeah.
most of them are generally related to the process parameters, so like the balling defect or the keyhole porosities, which normally it can be improved upon by even playing with the additive manufacturing process parameters. So, sir, in that aspect, sir, how does this laser polishing, how does this further improve upon those defects, sir? That's the question.
The voice got broke at the last. So can you please repeat the question, please?
Sir, some of these defects that you mentioned, sir, like balling and
Yes.
keyhole porosity, sir, they can be controlled by varying the process parameters, like by controlling the laser
Correct.
power and scan speed.
Correct.
So, sir, in that aspect, sir, do we need to go to laser polishing, or how does it further improve those on those defects?
Okay, you're Santosh, right? Santosh.
No, Pramod, sir.
Pramod. Okay, Pramod. See, Pramod, it is like this. Even in a lathe machine, you have a tool nose radius. The truth is, it has to replicate the tool nose radius surface onto the shaft, right? But whatever said and done, you always have a machine vibration will be there, tool wear will be there, workpiece inhomogeneity will be there. All these things will lead to defects. However controlled you do, you will still have this balling and then this staircase effect. All these things are part of it. Once you have all these things part of it, it is prone for such defects. See, all these things, whatever I said here, no? So you can
Yes,
see all these defects, whatever is seen here. Let me stop sharing and I will share it once again. So all these things, these are all taken in an SEM image. So they are all to the highest 200 microns. Okay, twice
yes,
of
sir.
the higher size. Look at it, partial melting will happen. All these things are part of the game. You cannot live without these defects.
Okay.
So even after doing all the process parameter optimization, you will have such defects. Now these defects and surface roughness has to be improved.
Yeah. Yes, sir. I could understand the surface roughness aspects. I just need some more clarity. Thank you, sir.
So there are a
Yes,
couple of questions. Yeah, Pramod, thank you. There are a couple of questions in the chat box. I will take it for you, sir.
Hi, please.
One is how can we use the laser polishing for intricate shapes or holes?
So here what happens is, whole internal is always a problem. Whole internal is a problem, but intricate shapes, what we do is we try to play with the focal plane. So the focal plane, what you do is when you keep it in the focal plane, maximum focus happens. Now you try to defocus, try to keep intricate shapes slightly far off. And then when you keep it defocusing, what happens? There is a larger radius. Now, if you try to control the feed rates, so then there will be 90% overlap, 80% overlap. Like that, you can try to do very small intricate shapes finishing.
Okay. Thank you. And the next question is on surface roughness related. How the as-built surface roughness taken into account for the simulation?
Pardon me,
Sir,
Subbu.
it's related to surface roughness related. How has built surface roughness of the material taken into the account for simulation?
Yeah. So that is what I showed you now. See, generally what we do is like, okay, so let me show you our model, whatever. See, this is what is the model we develop. So what we have to do is you have to take the flat surface, and on top of a flat surface, you have to try to generate random number. So in the random number, what you do is you say that what should be the range. It has to be from -1 to +1, and you give the range. And in the random number MATLAB, whatever you simulate, you try to give the XY value also. You say X varying from 0 to 100, Y varying 0 to 100, and in that plane, I will have a roughness which is varying from -1 to 1. You try to give this random number generation, and that random number generation, try to simulate it on top of your surface. Otherwise, you try to take the profile, try to take a grid profile. Okay, and then you try to get on an area, what is it is coming. So you get a small patch. Now you superimpose several of these patches and you can try to generate the surface. Like this you have to do.
Any other questions from the participants?
Sir, hello. I do have a question.
Please.
The major aspects of laser polishing on the processes shown here is related to only the surface.
Yes.
So, is there any processing that we can do that will reduce the gas holes or any other types of defects that will
See,
occur
laser polishing is only a surface polishing method. It is like powder applying to the face. You are only uplifting the face. If there are pores and porosities on the face surface, you can fill it up with the powder, or you can try to give a face upliftment to the powder, to the face. That's all. Internal defects curing is not possible by laser polishing method. We are only calling polishing only, no?
So that is what I'm asking. Is there any other methods to do for internal?
It is very difficult, sir. Suppose if there is a hole which is stuck inside, the gas has to be walled out. Until and unless you have a porous structure, nothing will happen. So it is not so easy.
Okay, sir. Thank you.
Yeah.
Thank you. So any other questions? Ponarasan, better you can unmute yourself and ask this question.
Ponarasan.
Yes.
If it is possible for laser powder bed fusion method, 1 millimeter thickness, after laser interaction, does it overlap hatching area, waviness from? Yes, Ponarasu. So if I understand correctly, layer thickness is 1, and then you are trying to, next time when you try to sink the bed, you are trying to put a second 1 millimeter layer. The laser will try to overlap and stitch both. So this is for a single spot we are talking about. Yes, it does it. Any other question?
Sir, good afternoon, sir. Nice talk, sir. Yes, sir. So thanks for your talk, sir. I have just one question, sir. Is it worth attempting making surface removal or polishing at the during the last track of the processing, sir? So let's say I'm making a component by powder bed fusion.
See, at that point, what you have to do, see, there are two things you are trying to mix up, Keshavan. One is you have a powder, whatever it is. Let us take a steel powder is there. For that steel powder melting, you have a laser, which you have a fixed process parameter. For example, flux, this, that. For laser polishing, if you are supposed to do, you are first supposed to understand the last surface, whatever you have generated. And accordingly, you can try to add or change your process parameters. So today there are laser machines wherein which the last deposition, whatever it does, it scans the roughness and it communicates back to the laser, and the laser tries to optimize the parameters and try to do it. It is possible, and it is also worthwhile for you to try and see in a machine.
Yes, sir. Yes, sir. Thank you, sir.
It is possible. If you have diffusion, it is also possible.
Okay.
Any other questions from the participant?
So I don't know if I have done justice, Subbu. So there are no questions. If they have not, if they have understood, excellent. If they have not understood, I'm sorry. I'm disappointed.
No, so it's like a great lecture, so if no more questions, then thanks, sir. Thanks for.
But I would suggest, please, all the research scholars, you try all these future trends, whatever I have placed it here. With the help of advanced characterization facilities, the depth analysis of 3D roughness. What I have done is only 2D. You have to now do 3D roughness. Okay. So whatever simulation I have shown in front of you is only 2D. These are all 2D. If you want to do 3D, that will be very interesting. Then you are supposed to keyhole regime produces surface waviness. So that also you please try to see. This is a new area. Not many publications are there. And these are all done for a flat surfaces. Suppose let us assume I have a radius like a globe. I want to see on the globe surface outer, how do I do it? So then it is completely a different phenomena. A hemisphere you can take. So many new things can be done. So there is a huge scope. Please try to use it. Okay. So yes, thank you very much, Subbu. Thank you for the opportunity. All right. I wish all the participants good luck, and including to Subbu, wish you good luck and a better future, Subbu.
Thank you, sir.
Thank you. Right.